Hello, in this video we'll talk about combination of prisms and their use cases. We'll just discuss two cases which are useful in many situations. We'll derive few formulas, but always know that in many optical instruments prism are used for many purposes such as changing the direction of light, etc. So one of the use case is basically in measuring refractive index of certain liquid or a medium, right? So here we have a special instrument called refractometers. So refractometer is an instrument by using which you try and measure the refractive indexes. So here we have a prism here, okay, whose angle of refraction theta is known, whose refractive index n1 is also known. Then we stick another prism on this surface whose refractive index n2, or we can fill it up with that liquid, etc., whose refractive index we want to find. So this is what we want to find out, and we send a ray of light like this, gets reflected and then observed on a screen at a distance L, which is known, and this is the height h which we can observe. Okay, so L is known and h we observe or is known. Okay, now as you said that the prism is going to deflect the light, and by measuring this delta, basically, we will be able to find n2. So we need to somehow find an equation for n2 and possibly a difference between n1 and n2. Yeah, then we can determine all that. So let's start. So basically, first thing first, we know that the ray of light is coming here, right? It is coming straight, so there is no refraction, so we do not worry about this point. Now we come here and there is a refraction of ray of light, and assume that there is a very small difference between n1 and n2. Okay, so we have two liquids, so let's say 1.5 and 1.51, right? And we want to know if there is a difference. So this difference is very small. Okay, so that is the assumption in this case. So now we have a ray of light coming like this. There is a refraction, so we can write Snell's law here. Okay, then another refraction over here, and then using this equation, we will be able to find delta and the relationship for n2. Okay, so first thing first, let's write the Snell's law at A and B. This coming like this has refractive index n1. Okay, sine of theta. Other side, n2, refractive index changed, sine of alpha. Okay, this is our first equation. Now at B, let's say after bending, the beta is the angle of incidence, so we can write n2 sine of beta is going to be equal to this deviation, and it's in air, right? So 1 into sine of delta, and this is equation number 2. Now we need to find n2, and we have to, like, whatever is common here, we have to just get rid of them. We can find delta with observation, right? So we'll keep that. Alpha and beta is unknown, theta is known, right? So theta is very simple. Theta is known because we know this angle of the prism, right? This is 90 degrees. This is going to be 90 minus theta, right? And because this is perpendicular, yeah, so this is going to be 90 minus theta. This is perpendicular, this is going to be theta. Okay, so theta is known, so theta will keep, Okay, so let's change the color. N1 is known, theta is known. Okay, delta we can measure, alpha is not known, beta is not known. Okay, so first we have to eliminate one of these and then find a relationship between beta or alpha and theta, and then we will be able to solve the equation. Okay, so this is how we'll think about this. So first thing first, let's try and find a relationship between alpha, beta and theta. Now beta is a this very small angle after deviation, and this is again normal, right? So when this meets in this triangle, basically, let's have a look. Okay, the line number one, this is the deviation. Okay, this is our perpendicular line. Let's move it parallel to it. Say that is very small. Okay, and we know that this one is alpha. Okay, and this one is beta. Yeah, and so this one's coming straight, so we'll draw this like that. But why? Straight line like this here. Yeah. So this is straight line. This is theta. So by just trying out few things, we are trying to find this relationship. This is what we have to do in unseen problem any which ways. So this is our theta. This is our beta, and these two will meet somewhere here. Okay. So this is going to be theta, and this is also going to be theta. Okay, and hence we'll find that alpha angle is slightly bigger than that, so alpha plus this angle over here, so this is our theta, this is our theta, so theta plus beta is going to be equal to alpha, right? So in this triangle, right, look here, we know this angle is theta, right? This angle is theta because these two lines are parallel to each other. Okay, and if this is theta, this is going to be theta. Let me mark it in different colors so that you can see it clearly. Okay, so this is a parallel lines. Okay, this line is like that, this angle is theta, so this angle will be theta. Okay, and now from here this is going like that, and this angle is beta, and this angle is alpha. So we know that in this triangle, theta plus beta plus this angle A is going to be 180, and this A plus alpha is also going to be 180 because this is a straight line. Hence theta plus beta is going to be alpha. Okay, makes sense. So now we are able to find the relationship between these three, and basically then we are going to solve this to find n1 n2. Okay, so very simple. Let's separate n1 n2 first. Okay, so we are going to be writing here n2 is sine delta from this equation, and n2 is also equal to n1 sine theta sine alpha. Okay, Okay. Now we know n1 and we need to find n2, right? Their difference. So what will be n1 minus n2? Very simple. n1 minus n2. N1 we know all this, and then n2 we have written over here is this one. So this will come out to be sine alpha sine theta minus 1. So in here, now we have this unknown beta here, which we are going to sort of get rid of by this relation of sine here, right? So we know that alpha is going to be equal to beta plus theta, right? So sine alpha, we substitute here, sine of alpha is going to be sine beta plus theta. Okay, hopefully somehow we can get rid of sine b. So let's write that down. This is simple. Sine beta cos theta plus cos beta into sine theta is going to be alpha. Now, one thing we know for sure, that because this refractive index are almost same, right? N1 is very close to N2. The beta is almost 0, right? It's tending towards 0. So beta is basically a very small angle. So we can write for small beta, when the beta is tending towards 0, cos of beta is going to be 1. So at beta very small, we have cos beta is equal to 1. So we are going to write cos theta plus sine theta, and we are going to plug it over here and find that value. So sine beta cos theta plus sine theta divided by sine theta minus 1, and that will give us, so go up, sine beta cos theta plus sine theta minus sine theta divided by sine theta, and that will be equal to sine beta divided by tan theta. Okay, so this expression over here will reduce to a very small number, and now we know that n1 minus n2 now will be n1 minus n2 will be sine delta by sine beta into what we have derived here, sine beta by tan theta, right? So sine beta tan theta, so go. Now we have n1 minus n2 for small angle beta is going to be equal to this. Okay, now we know that the deviation is also small, right? So this deviation which is happening here is also small. So in that case, we can simply write that for small delta, sine of delta is also equal to tan of delta, and is roughly is equal to delta itself. So that is going to be h by L. Okay, so we discussed this basic trigonometric identities when we were doing the first problem session. So if you have not watched it, please watch. So you will get here sine of delta by tan theta will be h by L tan theta, and that is n1 minus n2. Now all of it is known, right? So we know the n1 h, we can observe L we know, tan theta we know. Now we can find the refractive index n2, and this method is quite effective, so we can find difference up to 10 to the power minus 5 as well, right? So if you have two liquids, if you want to check that if they do they have a different refractive index, you can simply use this method to find that for you, and this is quite effective method. So I'm just trying to solve few problems for you so that you get an idea on how to think about solving them, and you can try it out yourself. This will make you more confident, in solving these problems, and that is what our objective is. So before we close the video, we want to talk about one more case, and this is important because a lot of questions will come uh, on this concept, right? So now let's get started on this one. So basically we have two small prism, or a small angle prism here. So prism number one, okay, so this is our prism number one. Then we have another one, right, with same theta, and we call them biprism because we now have two of them with a small angle. So we are going to write that theta is small, something like in the range of 2 degrees to, let's say, 5 6 7 degrees type. Okay, very small theta prism. We have a ray of light which is coming parallel, getting deviated by it, right? And then, so basically if we have a beam of light of width d, it will come here, will get deviated, cut, and basically on the screen at a distance l, it will be seen at a small d, and we need to find that what this delta is, right? So in case of prism, we are always interested in finding the deviation. Okay, so with this background, first thing first, we know in the previous case I have also shown that now this angle of incidence is going to be equal to theta, and you can simply derive that because this is 90, this is 90 minus theta, and then this is going to be theta. You can simply derive that yourself. And so as it is coming straight, nothing will happen. This ray will come pretty straight here all the way up to here, and the total, sorry, and then we can apply Snell's law at this point. Okay, so all the way the ray will come, hit the base, get into the prism, and then the reflection will happen over here, and we are going to write that equation of Snell's law here. Okay, first thing first is a bit is coming from air, so we are going to write 1 into sine theta. Sorry, now we are writing here, right? So it's not coming from here. You have this prism which has a refractive index n, so that was the wrong approach. And sine theta is going to be equal to, now this is our normal, right? So this is going to be angle of reflection alpha, so we are going to say 1 sine alpha. We have this equation. Okay, now we need to find this alpha somehow, because we can always relate it with this one. So now let's try and find out this alpha, right? So consider this ray, okay, and this is getting deviated. So this is our delta, right? So it is getting deviated. Now we have this triangle, okay, where, so now we have this triangle, and we need to find this ratio. We know this is L, okay, and we need to find this one, and then we can write tan of delta, right? But we need to first find this A, and this is very simple. This distance is going to be d by 2, and this one is going to be small d by 2. So this A we are looking for is equal to d plus d by 2. Okay, so we know this, and now tan theta, sorry, tan delta is going to be equal to this A divided by L. Okay, so tan delta is going to be d plus d by 2 L. This this delta is very small, so we can simply write this is small, so tan delta is going to be equal to delta, and we can write that here. It's going to be now delta is equal to A by L, right? And A we know is d plus d by 2. So this is our another equation by that approximation. And now let's look at the Snell's law equation which we wrote earlier. So sine theta and sine theta is sine alpha. Okay. Zoom out a little bit. You can see all the equations. Yes. So now let's look at the Snell's law equation, which is n sine theta is equal to sine alpha. Okay. So sine alpha by sine theta is equal to n. Now alpha here is nothing but theta plus delta. Okay, so we are going to substitute that. So alpha here is sine theta plus delta divided by sine theta. This is equal to n. Now we know that delta is small and theta is also small, so we can simply assume that they are equal. So we can simply write theta for small values. For small values of sine theta, it becomes theta. So theta plus delta divided by theta is going to be equal to 1 for small values, and therefore delta is going to be theta into n minus 1. Okay, so we can simply find the deviation like that, and we already this is a very important concept where whenever you have a prism, okay, we talk about any prism with very small refractive angle, like 1 to 5 6 degrees here, right? Very small angle. Angle theta, we can say that the deviation of ray of light from here, this delta, will be simply theta into n minus 1, right? Where theta is the small angle and n is the refractive index of prism. Okay, so this is a very important relationship which you possibly want to remember, because a lot of questions comes from this side. So we need to find d, right? So we have a relationship here which says that so delta is known now. Okay, so we will write here once again, writing delta is a by l. Okay, a we have already defined here, and now delta we know from the other side, which is going to be theta n minus 1 is a by l. Okay, this will go that side, l into theta n minus 1. This is going to be a, which is t plus t by 2. So multiply here, and finally we'll get our expression for t. So this is 2l theta n minus 1. We can find that what will be the size of this after deviation where the light rays will meet, and this is our t. So remember this, the important point here is basically the small angle approximation of the prism, and then the deviation becomes very simple. We are able to do that because with this small angle approximation, because of the symmetry of these two prisms on top of another, you know uh, This is the prism we use to derive the equation. The same will be applied here, right? For deriving d, but for a small angle prism, the deviation is equal to theta into n minus 1, and that's what we want to highlight. So we'll be doing more problems in the next session. Until then, goodbye and take care.